Now in this section, 7.2, we're getting into the molar mass, and we'll just be going over two concepts in this video. It's the molar mass and the percent composition. There's a little bit of math to go with each of these, but I'll show you examples of each of them so you fully understand how to do them and what we use it for. And so we know that there's a very special number that goes with what a mole is. It's just 6.02 times 10 to the 23rd, and this represents the number of particles. So remember that this number is extremely large, and it represents 6 hexillion particles. And we said that is useful because we don't have to worry about what the identity or how much it weighs for each type of substance. But we also said that it was convenient to count out things in terms of moles. So we said that counting individual atoms would be really, really difficult and very expensive. But also, when you think about it, counting out 1 hexillion things, that's also not really convenient. So that's why we also use the mole in a little bit of a different way. We use it in terms of mass too. And so we measure a lot of different substances just in terms of the mass, and depending on what that number for their mass is, tells us how many particles it will have in a certain weight. All right, so when we're counting the mass of a mole of whatever it is, we just call that the molar mass. And we'll look into a little bit more detail what goes into a molar mass. To bring it back to the example that we had in the last section, remember that I told you that we can have two different types of sports balls in this one. We can have baseballs and we have tennis balls. And if we just ask for a dozen of each, we know that we have 12 baseballs and 12 tennis balls. And now we know that we have the same number of each, we have the same amount, but as you probably know already, baseballs and tennis balls are not the same thing. They work a little bit differently. They have different properties. Tennis balls are a lot bouncier than baseballs, so playing a game of tennis with baseballs would actually be really difficult. But just like these two types of sports balls have different properties, all the elements we know also have different properties. And one property that we focus on especially is the atomic mass. Now, if you remember back from our atomic theory chapter, you know that the atomic mass accounts for the number of protons and the number of neutrons of an element, and we combine that into a single number. Now, we're bringing the molar mass into this mix, and so we're actually using the same number, but it's telling us different information about an element. And so for the molar mass, it tells us how much how much 1 mole of that element will weigh. To look up what the molar mass of any element is, you need a periodic table. And when you look it up on the periodic table, this is what you'll see for each different element. Right? You have the box, you have the symbol for each element. Here I have carbon and iron. I know what their atomic numbers will be, and then I also know their atomic masses. Here for carbon, it is 12.011, and for iron, it is 55.847. Now remember, this is the atomic mass of an element, but then when we're talking about moles, this is also the molar mass. This is what 1 mole of that element will weigh. And just some details to go into this for this one is that, again, molar masses are measured in the unit of grams per mole. And that's what this is telling us, that in 1 mole of that substance, I am weighing this many grams. Now, there's a lot of inconsistencies between periodic tables. Some will tell you the molar masses down to 6 decimal points, but for our purposes, we can just simplify that down a little bit and just focus on the first 2 decimal places and round off to that. So don't worry about giving me 6 decimal places, 10 decimal places. That's a little too much. We'll just stick with 2 decimal places. Now, if I just ask very simply, what is the molar mass of 1 mole of iron? You could just tell me that it is 55.85 grams in 1 mole. Now, it's very simple, but in chemistry and in the real world, it's very rare that we get to see just a pure element all by itself. More commonly, they're part of compounds, right? They're different elements mixed together. And so now this complicates things a little bit more because we can't just look up every element and every compound and know what their molar masses are. So we have to do a little bit of calculating on our part because we still count molar masses for compounds, but when we tell the molar mass, we need to account for every atom in that compound. And notice that I'm saying every atom, not just every element. You'll see what I mean in just a second. So if I have this compound over here, calcium nitrate, and I want to find its molar mass, this is what I would do. I would, that's a very neat way to organize this. I would set up this table, which is with atoms and molar masses, and I would just take it one element at a time. So if I focus first on calcium, I'll say that I have one calcium. That's what I mean about every atom. In this compound, there's only one calcium that's written in, so we'll just say that I have one calcium. If I go to the periodic table and find its molar mass, it is 40.08, and I multiply that by 1 because I only have one calcium atom. If I take the total, 40.08, I'm going to save that just for now, and I'll move on to the next element. Now, when we focus on nitrogen, this is where it gets a little bit more interesting, because notice here that I only have one nitrogen written, but it's inside of a parentheses with a 2 outside of it. So now remember, these subscripts outside of parentheses apply to both elements inside of that parentheses. So here, even though only one nitrogen is written, really I have two nitrogens because of that 2 subscript. So I'll add that to my list. I have 2 atoms of nitrogen. Now the weight of each nitrogen is 14.01. This is what I learned from the periodic table. And then I know there's 2 nitrogen atoms in this compound, so I have to multiply that mass by 2. Take the total of that, 28.01. And again, save that for later. We still have another element that we need to count for. So in this case, we have oxygen. In here, it's written as O3, so that automatically means 3 oxygen. But again, notice that there's a 2 subscript outside of the parentheses. So we're going to take this 2 and multiply into that number in the parentheses. So in this one, I have 2 times 3 gives me a total of 6 oxygen. And so now each oxygen is worth 16.00 grams, and I multiply that by 6 because I have 6 oxygen atoms total, and that gives me a mass of 96 for the oxygen. Now to find the molar mass of the compound overall, I just need to take all the different masses that I just calculated. I have to add them all together. And so if you take 40.08 and add a 28.01 and 96.00, the total that you get is 164.09, and that is the molar mass for this compound. Calcium nitrate has a molar mass of 164.09 grams per mole. And now finally we get into the percent composition for these different compounds. And so it's really nothing new. It's just taking a percent and showing us how much each element makes up of the total molar mass. All right, so again, there's nothing fancy about this. It's just a percent calculation where we're taking the part, dividing it by the whole amount, the total, and then we multiply it by 100 to get the percent out. So again, if we go back to this example and carry on with it, I already know the total mass, and I know the individual masses for each element. So let's use it to calculate. If we focus just on calcium, we will take 40.08. I said that too much. 40.08 and for the mass of the calcium, and I will divide that by the mass of the compound, 164.09. Divide that, multiply that by 100, and you get 24.43%. We move on to the next element for nitrogen. Again, the total of nitrogen in that compound, it is 28.01 grams, and I divide that by 164.09, multiply that by 100, and I get the result of 17.0% for nitrogen. And finally, when it comes to oxygen, let's see, the mass that I have for that oxygen total is 96, and I set that over the mass of the compound, 164.09, multiply that by 100, and I get the result of 58.50%. And one important check to see if you've done this correctly, remember that if we're talking about a percent, we're talking about a whole thing. The whole is really 100%. So your different percent composition results that you get for each element, they should all add up to 100%. And that is what happens in this one. We have 24.43 plus 17.07 plus 58.50. You get a total of 100. Now, there's a little bit of wiggle room if you do your calculations and you get to something like 99.6%. That will just be a rounding error that's throwing you off. That's still very close to the whole, but if you're off by more than 5 or 10%, then that means that you have some mistake in your calculation. You should go back and check on that. All right, but other than that wraps up just those two concepts: understanding what a molar mass is, how we get it, and then when we have different elements in a compound, finding the percent composition, knowing how much each element makes up of the total mass of the compound.